Hello there, and welcome to section 2.4 on arc length and surface area. So in this video, we're going to be taking a look at arc length. So arc length, as it says here, can be interpreted as the distance you would travel if you were walking along the path of a curve. All right, so that's pretty straightforward. It's the length of the curve. And so in this example right here, we have a curve. And in order to estimate the arc length, we can do it by creating line segments. Right? So if we had an arc length like this, we could create some line segments like right here, right there, right there, right there, to try to approximate it, because line segments are easy. We can calculate the distance of a line segment. So in this particular drawing, we have all these line segments, and so we're going to estimate the length of the curve by finding the length of some line segments. So finding the length of a line segment is easy to do with the Pythagorean Theorem down here. Now, I'll tell you right now, I skipped a lot of steps. If you're really interested in the full development of where this formula comes from, you may go to your textbook and it will give you all of the details on where that came from. But as far as being able to apply the arc length formula, I decided that we will just kind of skip some of that development for now. But it's based on the Pythagorean Theorem. So we want to find the distance of that line segment. Well, we can break it down into a horizontal component and a vertical component. And of course, then we have a right triangle. And so we can find the length of the hypotenuse of the triangle, which is our distance, by using the Pythagorean Theorem. Then if you throw in a little bit of algebra and the mean value theorem from calculus, you end up with this particular formula for the length of one line segment. Right? So keep that in mind. Back to our little drawing here. We realize, of course, that this is pretty inaccurate, that the line segments aren't even close to the actual arc length. So we do what we always do. We can create more line segments by creating smaller distances here. In other words, we're going to essentially, we have trapezoids is what we have here. Each one of these areas is basically a trapezoid. And so we create not fewer or more rectangles, but more trapezoids. And we get a more accurate approximation. So in other words, we have a line segment. Instead of one big line segment here, we're going to have a couple of smaller line segments. And then we could break that up even more if we wanted to into a bunch of smaller line segments. So how many line segments can we break it into? Well, we could approach infinity, of course. We're going to take the good old limit. And so that's what we do down here. So we have our arc length formula right here. And then we sum up all of those arc lengths and we get the total arc length of the curve. And we want a more accurate representation, then we let the number of trapezoids increase. In other words, we let n approach infinity. We take the limit as n approaches infinity of the sum of the arc lengths, and we end up with this nice little integral right here. Actually, it's not a nice little integral at all. It's a terrible little integral. It's got a radical in it. So the integral from a to b of the square root of 1 plus f prime of x squared dx. So that is our arc length formula. And we can see that right here in the box. All right, so that's our arc length formula. That's the formula that we're going to use. Again, I skipped some steps in the development of the formula. If you're interested in that, go to your OpenStax textbook and you can become more familiar with that. Okay, exercise 1, we have a function and we want to find the arc length over the interval from 0 to 1. Round the answer to 3 decimal places. So the steps that I like to take when I'm doing one of these problems is, of course, I'm going to start with my function. F of x is equal to 2x to the 3 halves. Then I find the derivative. The derivative of that is 3x to the 1 half. And then I square it. So 3x to the 1 half squared is 9x. So I do those things, boom, 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 just get that out of the way. I also find my bounds. Make sure you know what your bounds are. That was pretty easy. We were given the bounds in this particular case. And so now we can put all of this together in our integral, right? Into this formula right here. So bring that formula down here. The arc length from 0 to 1, square root of 1 plus f prime of x squared, which is just 9x. So that works out fairly nicely. Now, as a warning, some of these do not work out nicely. And you may find a problem in the homework that is not doable. If you do, bring it to my attention and we will omit that particular one. So how do we integrate this? Well, we have to use U-Substitution. We've been doing a little bit more of that lately. And so I like to do my U-Substitution over here on the side. If we let u be equal to 1 plus 9x, taking the derivative of both sides of this, the derivative of u is du, the derivative of 1 plus 9x is 9dx. And then solving that for dx, we get dx is equal to du over 9. I also like to take my bounds. My bounds are in terms of x, and let's convert those to u's. It makes it a little bit easier to do. So when x is 0, we get u is equal to 1. When x is 1, we get u is equal to 10. So now let's substitute everything in. So we have the integral from 1/9 u to the 1 half, right? Because u is 1 plus 9x, and the square root of that is the same as the 1 half power times du. And now taking the antiderivative of that, we get u to the 3 halves times 2/3. And notice that now I'm using my new u bounds over here. And I'm keeping everything in terms of u. If you do this, you don't need to convert back into x's again, which is just an extra annoying step. All right, from there, it's just plug and chug. And you end up with the arc length is 2.268. Example number 2. Now, I did this one a couple of different ways because this is just a straight line. F of x is equal to 3x minus 2. Calculate the arc length over the interval from -3 to 2. So going through the steps, like I said I always do, here's my function. Here's the derivative of the function. Derivative of 3x minus 2 is just 3. And squaring both sides, we get 9. Putting that into my formula, we have 1 plus f prime of x squared. 1 plus 9 is 10. And so that's just a constant, so that can come out in front. And so the integral of 1 dx is x. So we have radical 10 x evaluated from 2 to -3. And we end up with 5 radical 10. So that was actually pretty easy, pretty straightforward. So I decided, well, let's do this using the good old-fashioned distance formula, because we have this function 3x minus 2. So what would that look like on a graph? So here's The intercept is 2. We have a slope of 3. So here's a graph. It looks something like that. All right, with a slope of 3. And so we're integrating it from -3 to 2, which would be like somewhere over here to 2. And we want to find the arc length. So all we're doing to find the arc length, what are we finding? We're just finding the length of a straight line from so here's 3, here's -2. So we're finding this distance right here. So if we use the distance formula, which I wrote here, in case you don't remember the distance formula, it's the square root of x2 minus x1 squared plus y2 minus y1 squared. And so you need to, these are the x values. To find the y values, you plug those into your functions. So when x is equal to 2, you get 3 times 2 is 6 minus 2 is 4. All right, so you've got the 0.24. So that's where your y value here of 4 comes from. And when x is -3, you get 3 times -3 is -9 minus 2 is a -11. So you get that y value there. So you just find the y values using some algebra. And so you'll see that you get the same answer using algebra that you do using calculus, which of course you should. Next up, example number 3. Now, this one says use Desmos to calculate the arc length of the graph. I'm not sure why. We don't really need to use Desmos. Sometimes the directions will say to use Desmos or some graphing technology because you can't actually integrate it. There are some problems where we don't actually know how to integrate yet. That comes up in the next chapter. And so we're going to learn more techniques of integration that we don't know yet. So every once in a while, a problem sneaks up that we don't quite know how to do. So let's just go through the process here. Once again, I start with my function. I find the derivative of the function. I square the derivative of the function. And then I put it into my integral. All right, so we have the arc length is the integral from 0 to 1 of the square root of 1 plus 36x dx. So once again, we have to use U-substitution here. So I did that over here. U is 1 plus 36x. Taking the derivative of both sides, we get du equals 36x. Solving for dx is equal to du over 36. Plugging that in here, u to the 1/2. And then that brings that 36 out here. That du over 36 becomes a 1 over 36 times the integral from 0 to 1 of u to the 1/2 du. Now we actually find the antiderivative, which is u to the 3/2 times 2/3 times the 1/36, and evaluate it from, and I changed my bounds to u bounds again. So I took my 0 and my 1, my x values, and I plugged them in right there, and I got my new bounds in terms of u. And again, we do that so that we don't need to convert these u's back into x's again to get the final answer. You'll get the same thing either way, just like a couple steps less. All right, so now we just do a lot of plug and chug. Be very careful. You're going to see this a bunch of times, some number to the 3/2 power. All right, so that can be simplified to 37 radical 37. And so minus the 1 times 154 is our final answer. Now, if you wanted to actually use Desmos, you can do what we've been doing right along. You can plug this into Desmos and get a decimal number. And then you can go to your original integral, plug that into Desmos. And what you get as a decimal number for these two things should, of course, be the same. Sometimes, as we have done with volumes, we want to work with, rather than y being a function of x, what happens if we have a function where x is a function of y? We've seen that numerous times. Well, the formula is the same. It's just that we're doing it in relationship to the y-axis rather than the x-axis. And you have to keep that in mind. So the c and the d, the bounds of integration, are along the y-axis. And other than that, our function here has to be x as a function of y. Everything else is pretty much the same. So this was actually a rather simple problem because this is one of those problems we can't integrate. So I start with my function, x is equal to 3y cubed. Find the derivative, 9y squared. Square that, 81y to the fourth. And so we plug that into the formula for arc length, and we get our integral. So you can just plug that in the decimals, and it'll give you an answer of 21.03. Now, we will learn how to integrate an integrand like that in the next chapter. So something for you to look forward to. Okay, that is it for this video. In the next video, we are going to take a look at surfaces of revolution.